Good morning, everyone.
Morning.
As was said, I'm William Dula. I'm a senior mathematics major at Morehouse College, graduating senior. So this project was work I did as part of the High Performance Computing Facilities research experience for undergraduates at the University of Maryland, Baltimore County. That is a client-based and team-oriented research program where undergraduates get to work with faculty mentors to solve a client's problem and in the process answer some new questions that are being brought up. I highly encourage all of your students to apply for that program. It's a great experience. This particular problem was proposed by our client, Dr. Yuri Tosh, who's a professor emeritus at UMBC in the Mechanical Engineering Department. For the last 20 years, I'd say, he's been working on trying to find a solution to lameness in cows. And lameness in cows is a condition wherein a cow has pain in their limbs, and when there's too much pain in the limbs, they don't want to move, which means that they don't eat, and when they don't eat, they don't produce milk, which results in loss of productivity and increasing costs for the farmers as they have to bring in vets to treat them. So his primary goal is early detection. He wants to understand what are the important factors in lameness and how do we detect it early in livestock. And he did this by developing a machine, which will be on the next slide, that takes measurements, force measurements, and later on accelerometer readings of a cow's gait. So as it walks across the machine, it takes these measurements in all three dimensions, and it splits that up into 76 what he calls limb movement variables. Each one has a left side and a right side, to talk about the left side of the cow and the right side of the cow. And then that data is coupled with the veterinarian's assessment of whether or not that cow is lame or not. And these observations are created as the cows walk back from their milking stalls to their where they live. They're collected as they walk back through, and this is done about 3 to 4 times a day during collection days. All right, so this is a picture of a cow walking through the device. You can see it's kind of like 2 panels. I don't know if you can see that. It's kind of 2 panels that float, and as the cow walks by, it allows it to take measurements on the left and the right side. And again, these are sorted into these various. Again, these are sorted in these various categories, such as maximum force, average force, impulse, energy, and the stance time, how long the cow stood on each side, and a host of others. So initially, this was a simple logistic regression. It would just take all this data and run it through a logistic regression to see what the probability that the cow is actually lame is. And that was okay. It wasn't the best possible thing. As you would imagine, with such a high dimension of variable space, there were multicollinearity issues. And so we had to transform the data. Well, my advisor had to transform the data over the last few years and find methods to transform the data in order to eliminate that issue. And he did this using the procedure called transreg in SAS. Transreg is a pretty nice function in SAS. You tell it what kind of transformation you want to use, what variables you want to transform, and then it does it and it puts it in a new data set for you to use. So it's pretty quick, pretty easy. But the problem is SAS is a proprietary software. You have to pay to license it, and it's not cheap. So if you want to expand your business, you want to expand your model, you want to have more people working on it, you don't want to pay for multiple licenses. So you have to move to something open source. So one of our first goals was to bring these models over to R, an open source software. And also, SAS has some issues where you can't really explore a wide variety of models. It kind of has models built in, and you hope that with the next update they just put in the model you want. You don't really get that much say in how you do your analysis. All right, so our goals. We want to create this early detection model. That's always been the goal of the entire project. But we want to bring it over to R, so we want to hopefully try to translate it, and if we can't translate it, write something that closely mirrors what we were getting out of SAS. And then our client, in the course of doing our research, said what would be really helpful is if instead of just saying whether or not the cow was healthy or lame, if you could tell me if it was close to becoming lame or feeling some sort of pain, that would be really helpful. So we created a third classification called mildly lame. Then we want to maximize sensitivity, specificity, and the area under the curve. We'll go into depth in those a little later on, but those are three metrics through which diagnostic systems are measured, and we want to maximize those things. All right, so first things first, transformations. Transreg. As I said, SAS is proprietary, so they're not going to tell you how they do anything. They're going to tell you where they get their information. They're going to tell you what the options are, but they're not going to give you the bare bones. They're not going to give you the meat of their functions. So our primary task in the beginning of our project was to reverse engineer this transreg procedure. And initially, in SAS, they chose to use linear splines with 4 interior knots. So that's 4 places where the transformation switches across the data. And this is what that would look like. At the bottom is plotted the original data, and at the top or on the vertical axis, you get the transformed data. And so you see it's kind of plotting the original data to a line, and then it gets to a point, and then it switches to using another line, and that's kind of typical of how splines happen. And by default in SAS, as we came to find out, these particular cutoff points where you switch between different transformations are just the quantiles. So if you pick 4 interior knots, it's going to split it up into 5 equal chunks of the data. So that would be the 20th percent of the data at that first line, then the 40th, then the 60th, the 80th, and the 100 at the end. Okay, so we have to figure out how this is doing this. And we know that in their particular model that they were using, they decided to go with splines, linear splines, 4 interior knots. So we had to generalize this. We know the ideas behind splines. It's a very well-known thing. So we want to kind of generalize that, talk about this in terms of piecewise linear functions. So we know that these were continuous, at least in their implementation of the function, they were continuous splines. So we know that that's one constraint that we have. We don't have to find all these free parameters at the end of our linear functions. We just know if we can find one, we can say, okay, this has to be equal here, which has to be equal here, which has to be equal here. We can solve for the rest. So we're going to use this continuity to constrain our parameters. Then we can create a design matrix A, which will be our coefficients of our various linear functions for each predictor. And we have to do this once for each variable. And so you'll be able to actually see the structure of the matrix in a few slides, and you'll see why that matters. Then we have our unknown vector, theta, which consists of our coefficients that we're trying to estimate. Because we don't know what the actual transformation SAS is doing is. We're trying to recover that information. We know what the output was, we know what the input was. So we're trying to get that back so then we can go on and do our own analysis. All right, then we have this y hat. Y hat is the estimated response variable. It turns out, and this was believed to be the case, we still don't have real concrete proof of this claim, but we believe that this transreg procedure actually allows this y hat to be a predetermined output of logistic regression on the variable. So it's trying to optimize a transformation to something it already knows to be true, which is, from a methodological standpoint, kind of iffy, kind of shaky. So since SAS has been around for 30 years, we decided not to question them on that. And we decided that we would try it with this idea of having a logistic regression being your helper variable that you're using to help you estimate things. And we decided to do it without that, so using what the veterinarian recommended for each observation. And so if we do some matrix algebra, we get this equation where our estimated parameter is equal to the inverse of A transpose times A transpose times Y. And that will hopefully give us some values. Well, that will collapse down to a vector of values that we can use as our coefficients in this transformation. And then once we have those, we can go back and apply that to new data. All right. So that wasn't really enough. Part of our job was to improve the model. And on the back end, that's really not possible doing from the analysis side, so we have to do it from the transformation side. And so we decided to toy around with these transformations. So we already had it continuous. We could think of a conceptual model for that. Discontinuous, pretty easy. You just loosen the constraints. Now you have to add a whole nother however many columns to your matrix where you're also estimating these coefficients for each linear function. And then we tried it with cubic splines. Not too bad. Again, adding more columns, adding more variables in, and you're really just toying around with block diagonal matrices. So there's a lot of information on that. That's doable. All right. So now that we have our transformations, we've gotten this transformed data. We have to actually perform an analysis with it. And then we have to evaluate our analysis, evaluate our model to see how it was doing. And I'm going to talk about how we measure how good our model is, how good we were predicting. This is done with something called the receiver operating characteristic curve in medicine or in any diagnostic systems, classification systems. This comes up, and the idea is that you can make a graph, or you can make a curve, a discrete curve, by taking different points where you take your contingency table of possible events and you say, we're going to put this in our positive class if it's above a certain percent. Otherwise, we're going to put it in the negative class. And you just raise that percentage a bunch of times. So we start with 1%, anything above 1%, anything predicted to be above 1%, we're going to call that a lame cow. Anything below, that's a healthy cow. And then we're going to raise that up to 99%. And so we get all these data points of the true positive rate and the false positive, the true negative rate. And then we can plot these points. And if we plot the true positive rate versus 1 minus the true negative rate, which would be your false positive rate, you get the receiver operating characteristic curve. And this curve, this is an example of the curve. This curve and the area under it describes how good your model is. So if this was a straight line, then the area under that curve, we apply the trapezoid rule, would just be 50. It would be 50%. And that would mean that our model has zero clue what is going on. It is randomly deciding what each thing should be labeled. If it's a square, kind of like a rectangle going right up the y-axis and over, then the area under our curve is 1. That means we have created a perfect classifier that in all situations knows what is right and what is wrong. Not really possible, but we're aiming for that. We want to maximize this area because this area, from a probabilistic standpoint, represents the probability that our model is ranking positive out, randomly chosen positive instances above randomly chosen negative instances. And that's very important when you're having something that's classifying the health of an animal. And so this is a useful tool in all manners of diagnostics, but we just care about health right now. The issue is that our client wanted us to extend this. So when you have 3 classes to pick from, that means your model has now 6 different ways to mess up. And it turns out there's a whole field of probability where you talk about ROC, where they talk about ROC curve analysis and the different forms that come up. And it turns out that the dimension of this curve is exactly equal to the number of ways your model can be wrong. So when we move from a 2-class diagnostic system to a 3-class diagnostic system, we're moving from trying to integrate across a 2-dimensional curve to a 6-dimensional curve. That's not fun. That's not computationally efficient. R doesn't really do that because it was not designed by computer scientists or mathematicians. It was designed by statisticians. So we have to bring it back down. We got to bring it back down to 2 and 3 dimensions where it's digestible, and it can be done in a time where the high-performance computing cluster won't kick us off of the system. And when you have lots of jobs to run for lots of different transformations, and this all has to be done multiple times, you want this to be done very quickly. I believe our longest job took 23 hours and 40 minutes. And the maximum for us was 24 hours. So you can see we're kind of crunching for time. So this is how we decided, or how we chose to bring it back down to 2 dimensions. I looked all over these various papers in this area and found one result by Provost and Domingos, where they decided that if you split up the curve and look at it from planar cross sections, so you say we're only going to look at it from, we're only going to consider these 2 classes, and then we're only going to consider these 2 classes, and we're only going to consider these 2 classes. If you look at that, you can take an average of those curves, the area under those curves, and that'll give you a reasonable approximation of the volume under the entire surface. And so that's what we did. And theirs, it's a little different, where they decide to say, pick one class, make that positive, make everything else negative, construct your curve in that fashion for all 3 classes, take a weighted average based on the prevalence of each class in the data. And so you take a weighted sum of those, and that gives you a fair approximation for your area under the curve, which is really a volume under a surface at this point. All right, so now we know how our model's doing, and we'll get back to that. You'll get to see exactly where some of our results come from in that arena. Now that we have that, we have to build a model. Building a model in this case meant that we had to do some learning, because we didn't know what variables were important. And actually, looking through the data, there were some variables that just don't matter. You don't really care about maximum acceleration of a cow. Who knew? But that was so that's why this process, this learning process, is important. It's called forward variable selection, and the idea is that you create, you have some criteria by which you're going to evaluate your models, and for us that was this area under the curve that I talked about previously. And you're going to create P one variable models, where P is all your possible variables to choose from. Then you're going to evaluate them, which means calculating the AUC of each model. So in our case, it's 76 variables. Cool. Well, 76 times 2, because each one has a left variable and a right variable. You're going to pick the best one. Pick the one that performed the best. Now you're going to take that one and add every other variable to it. So you're going to create P minus 1, 2 variable models, which include the variable that we selected previously. Evaluate it, and we're going to repeat this until we run out of variables. And then we're going to go back through the list and say which one performed best. Out of all of these top performing things at these various numbers of variables, which one is the absolute best? This will be our final model. These variables will what we deem to be most important for our model. And so we're going to repeat this until all variables are added. And this is a typical forward variable selection. But our client, wanted to be able to say to the farmers, he wanted to be able to say acceleration is important, impulse is important, brake is important. He didn't want to have to say acceleration on the left side, brake on the right side, brake on the back right. He didn't want to be able to say that, or have to say that. So we had to kind of rethink how this algorithm works in order to do it for pairs, which amounted to us reorganizing our data and working with the algorithm to say, okay, we're going to pick these 2 columns and then pick these next 2 columns. But it had to be done in that fashion. And it actually made it go quite a lot faster. So what you end up with is P pairs of variables. All right, so this is our optimal model. This is actually the ROC curve for our optimal model. I'm not going to tell you what's in it. This is confidential. But I can tell you that the area under the curve using this data set was 84.32%. So it is 84.32% likely to rank randomly chosen positive outcomes above randomly chosen negative outcomes. It's pretty good. Because coming out of SAS, we were getting 70s, high 60s. It's pretty solid. Pretty solid stuff. now, looking at this forward variable selection, ranking all the different transformations over all the possible ways we could have chosen those variables, we see that, all right, so SAS is in orange. I don't know if that's too hard to see. It's kind of pitiful. But our logistic optimization, that's using SAS's idea that we can use our helper variable to be the output of logistic regression that we predetermine with the data, and we're using non-continuous linear splines. If we do that, we get good results, and that results in this 84-ish% that I talked about in the previous slide, and that occurs around 15 variables, 15 pairs of variables. Yes, maybe it's 14. It's 15 or 14 variables, and that's all you really need for this model. And so that makes things a lot easier, because then that means he only has to measure those 15 or 14 things. However, for each farm, it'll be different what matters, so you have to do this process for each new farm you want to bring the machine to. And then multinomial. All right, the real cheese. Our client, this is what our client really wanted, but we had to do both just to say, hey, this one's a little higher. I don't know if you want to go with this one. I don't know if you really want to expand this to 3 classes. But again, this table represents the idea from Provost and Domingos that you pick one class to be positive, and everything else, we don't want that. And then you construct that with this. And so this is that that process occurring for the sound class, so healthy cows versus everyone else. And then, okay, on a longer version, we added the ones for the rest of them, but to shorten it for time, we excluded those. But you can see how this might work. You just pick one class, compare that to everything else, pick another class, compare that to everything else, and this generalizes to an infinite number of classes. However, the problem is that as you spread out your classes, you kind of dilute the model in some sense. It's just because you have more choices, there's more things to be wrong, it adds confusion, and so that brings the AUC down about 4% from what we had previously. So on this, it hits like 80.1%, I believe. But the exact same transformation, that logistic optimization with non-continuous linear splines, we're doing way better than SAS. About 10, in the worst case scenario, about 10 points better than SAS. So this is good stuff. Methodologically, that's a big improvement on just dumping in data in SAS and hoping you get something good out of it. 3? Okay. And so our conclusions. I guess to sum up everything we did this summer, we found a methodology and a particular logistic regression algorithm to use with these linear splines that performs better than transreg. We were able to extend to multiple classes, or a higher number of classes, and in general we could extend to however many classes we so choose. But the AUC drops with every class we add. That's okay. And then we were able to actually create this early detection predictive model and give our client final recommendations on a new set of data with more cows. So that is everything that we did in a nutshell. And I guess the future work is really expanding our choices for transformations, parallelizing things to make it a little faster, and finding a way to put it on the machine itself so it can all be done on site at the farms. And so that is how to detect bovine lameness using 3-dimensional force analysis to achieve high sensitivity and specificity. Thank you.
Are there any questions for our speaker?
So you set up these models using some big collection of data they've given you in the first place.
Mm-hmm.
Did you have a chance to then try out the model on new data, or?
Yes.
Ooh,
about 2 days before we were supposed to, well, not 2 days, yeah, 2 days before we were supposed to submit our tech report, our client sent us 700 more cows. And he said, run the data on this. And we changed the machine. He changed the machine from using load cells to calculate data to accelerometers. And if I go back, the linear optimization, so not using the logistic, but still non-continuous splines, that ended up being the best on that one. So it does depend on how you measure. It seems to depend on how you measure the data, the cows that are there, and the particular farm you go to. Because for some farms it's going to be different because I guess you could say the families are different. We talk about familial health and all that, but yeah.
Any other questions for our speaker?
So can you maybe walk us through how long it takes? Let's say if a cow actually goes to the machine, you actually collect the data. Between that and then actually running the algorithm and getting the results, roughly how long would that take?
Right now, so the cow can walk across the machine in under 5 seconds. And that data is recorded and stored. Then it's really however long it takes Dr. Tash's grad student to sort through the data and label everything. That usually takes him 4 days. And then running, once you have the model, it only takes like 2 hours, 2-3 hours to run. At least on 700 cows, that's what we found out. It only took like 2 or 3 hours to run. Of course, that was on a supercomputer, but so yeah, it might take a week to get it back. And our hope is that we'll be able to find a way to make it fast enough and simple enough to just run on a laptop so they can just do it right at the farm. And that comes down to some more design choices about how they choose to collect the data and organize the data from the machine. Because right now it just comes out as a bunch of numbers, but it takes about a week.
So have they used so the results that sort of predictive they improved? Have they used them in any way to?
With the fresher data set, I believe he made some recommendations. Let's see, we gave him that in August, the beginning of August. So yes, he should have gone back to the farm at least twice by now. So we should have been able to use this. And all these measurements were taken from the same farm, so we didn't have to redo. The analysis, but we made very nice documentation for him, so he can redo the analysis if he needs to at another farm. So I believe he has used it. And typically, what he does is he invites a veterinarian to come as he comes to collect the data to help out. So.
William was an excellent talk, and I certainly enjoyed it. And one of the first things that I thought of is the lameness that I had in my left hip. As well, very articulate individual. And I'm probably the only one in the room that did not understand everything that you said in your talk. But you mentioned a couple of words that I probably would like my students to heard before, and that I just want to kind of query you about a little bit actually about. It just looked like in some of the calculations I saw a matrix, you don't have to go back to this is just talk. And you might even have an inverse on that as well. Do all matrices have inverses, or do we have to worry about that at all?
We do have to worry about that. That's why the ATA was in there, because we had to construct an inverse matrix. So that's why that A transpose A was in there. But yeah, we had to construct an inverse. That's why that was there, because the way we set it up, it wasn't even square. Turns out not to be square. It's however many transformations you have by however many observations you have. So that was like, or however many pieces you have by the number of observations. So that was 5 by 395 in that data set. And so you have to construct that. You have to construct a square one out of that.
I think there somewhere I saw a couple of summation signs as well, and I take it that these are all finite sums.
Oh yeah.
Nothing was negative sum.
It's only like two. When it comes down to it, you're only really adding like 2 or 3 things together, 2 or 3 numbers. Yeah, we just wrote it like that because
Looks better.
yeah, it's fancy.
And you mentioned something about splines and then it being continuous or whatever. I didn't quite understand that word continuous.
So
Kind of means a little bit.
the splines, so the splines are a way to describe data by sectioning it off and making different sections of the data kind of have their own function to describe them. If that makes sense. And a continuous spline is the idea that the function from one section and the function from another section, where at the point of where they switch, there's no discontinuity. And depending on what order of splines you use, like cubic, or well, most people just stick with cubic and lower, then you have to talk about, okay, what do we mean by continuous? Do we mean continuous just continuity as in it's not broken? Do we mean continuous over the first derivatives, continuous over the second derivatives? And I think in our thing, we chose to make it just continuous in terms of there was not a gap between them. And we didn't try to specify saying we want it to be first derivative continuous and second derivative continuous, mostly because that just took a lot more computations.
I take it that when you started this on this particular research ventures with others, that you've never heard about this stuff.
Yeah, this was the first time I've ever really interacted with statistics in this way. I didn't take statistics at Morehouse because I was scared of it. But it kind of opened my eyes. I had a great group of people to be around to help me learn stuff, and I was one of the older people, so I was kind of like in that mode, like I'm just going to learn it. I got to do it because it has to get done. And we had great teachers. My advisor just helped out and gave us so much support in trying to learn what we needed to learn to solve this problem. And he took a very, I don't know, he was kind of hands-off. He said, I'll help you figure out what you need to learn. From there, it's all you. Take whatever path you deem fit to solve the problem. So.
And that was one of my questions, whether or not you had statistics for people or not. What classes, I take it that you kind of came up here, got involved in this, and you were a mathematician, a group of others. So what classes have you had that you said to yourself, wow, I'm glad I had that class?
For this particular thing, I'd say my year of analysis helped. I had a year of analysis. I also had a year of linear algebra. We don't actually offer a year of linear algebra, but one of our electives was advanced linear algebra, and we ended up touching on a lot of topics, a lot of like linear spaces and more like early grad linear algebra stuff that came real handy doing these transformations and trying to figure out some of these equations and solve some of this stuff. So.
Let's thank our speaker.